Okay, so good evening, everyone. Welcome to another Wednesday seminar. Today we have the pleasure of hosting Dr. Silvia Spezzano. So Dr. Spezzano is a truly multidisciplinary scientist. She does both lab work and astronomical observations. And so she started her career as a chemist. So from 2003 to 2008, she studied chemistry at the University of Bologna. Then when she graduated in 2009, she moved to the CFA for a one-year postgraduate fellowship with Mike McCarthy. And then in 2010, she moved to Germany at the University of Cologne and the Max Planck Institute for Radio Astronomy in Bonn, where she did her PhD with Stefan Schlemmer and Carl Menten. From 2013 to 2015, she was a postdoc at the University of Cologne, where she also took a parental leave. And then in 2015, she moved to Munich at the MPE to work in the group of Paola Caselli. So she did a postdoc from 2015 to 2017. And in 2017, she won a very prestigious grant. She became a Minerva Fast Track Fellow at the MPE. She also took her second parental leave. And then since November 2020, she has won another very prestigious grant, and she's now a Max Planck Research Group Leader at the MP. So today she will talk to us about her group's research directions. And so without further ado, Sylvia, the floor is yours.
Thank you, John. Can you hear me well?
Yes, we can hear you.
Okay. Thanks for the nice introduction, and thanks for inviting me. I'm very happy to be able to give a talk today. I'd be happier to be there, of course, but this is life now, so I hope I can come and visit you in the future. So today I will talk about chemical complexity at the dawn of star formation. I will give you an introduction of why we use molecules to study star-forming regions, what are their peculiarity, why are they important, and then I will dive into my research. In particular, I will talk only about my observations, so I will not talk about the laboratory work because I don't have the time. But I'm happy if you have any questions about the lab and curiosity. I'm happy to answer questions about those as well. Please feel free to interrupt me during the talk if you have any question, if something is not clear. Just unmute yourself and interrupt me. I might not see you if you raise your hand, but feel free to interrupt me. So let's start. Can I start? Yeah. So let's start with this beautiful image that shows you the different phases in the evolution of a diffuse cloud down to the formation of a protostar and then eventually a planetary system. So in my research, I study the evolution of material from one stage to the next in the formation of stars and planetary systems. I study how the molecules are inherited from one stage to the next. What you have here, you go from diffuse cloud to dense cloud, and then in dense clumps within dense clouds is where stars are formed. And you have here young protostars still accreting material from the accretion disk, where then the planetary system will eventually form. So what is not pictured in this image is that towards the end of its life, the star will eject material in the surrounding environment and will basically close the cycle here, and this material will rejoin the interstellar medium and then go back into this cycle. In my research, I particularly focus on the earliest phases in star formation, namely starless, prestellar, and protostellar cores. So starless cores do not have a central heating source, so the protostar is not yet formed. They are not gravitationally bound, and they might either evolve into a prestellar core and then form a protostar, but they also just dissolve back into the interstellar medium. Prestellar core instead are more evolved starless cores. They still don't have a central heating source, but they are gravitationally bound, and we do see observationally, we do see that they are infalling towards the center. So the collapse is already started, although it's very slow. So the collapse in prestellar cores is the subsonic, it's very slow. But they will for sure evolve into a protostellar core. So they are on the verge of forming a protostar. And then there are the protostellar cores. So a protostar is a very young star. There is still accreting material from the envelope. Of course, the central heating source is present, and the protoplanetary disk is formed and is evolving. And we have actually hints from observations, from other observations, that also in very young protostellar cores, so already class 0 and young class 1s, we can already see the gaps, the hints of gaps in the protoplanetary disk, maybe hinting at the fact that planets start forming very, very early in the evolution. So as I said, I work on mostly on the early phases in star formation, but in my current group, one of my short-term plans is to make a link to exoplanets. Now, I don't have to explain why exoplanets are important and interesting. They have boomed in our community in the last years. Since the first exoplanet was discovered, thousands of exoplanets have been discovered, have been observed. And so my aim is to make a link and to start making this link from the laboratory. So this is how I started working in the star formation community, because I had observed a molecule in the lab for the first time, and then I wanted to observe it in space, so I did the observations. And I would like to do the same transition with exoplanets. So I will start by providing spectroscopic data, in particular of infrared spectra at high temperature of different molecules for the observations, for the future missions that will observe the planetary atmospheres around exoplanets. And then eventually, but this is a mid, longer term goal, I would like also to move into observation of exoplanets. So my goal is really to find the link, to find the chemical connection in between all of these stages. And this includes also exoplanets. Now, the connection from early phases in star formation and exoplanets might seem far-fetched, but it is not. And I want to make an example just to show you that it is indeed the real connection. So the early phases of star formation, actually prestellar cores in particular, are extremely important. So obviously all the material that will then form a planet is already present, from the organic molecules that will form the prebiotic material to the solid part that then will form the refractory part of the planet. The question is how much of this material will stay intact in the formation, during the formation of the protostar, and then in the evolution of the protoplanetary disk. And the question is, the switch on of the protostar, does it set the chemical clock back to zero? Do we start really back from zero? Or is there some memory? And there are several studies that show that there is indeed a memory, and there is quite a track that we can follow from the prestellar core to planets. The one notable example that I want to show you here, it's about water. So this is referring to a study from Ilse Cliffs from 2014, where she modeled the formation and deuteration of water in the solar system. So she wanted to reproduce the enhancement that we see in the deuterium in water in the solar system. We see that also in our own planet. The water in our oceans are enriched in deuterium with respect to what one would expect just by looking at the deuterium to hydrogen cosmic isotopic ratio. So she did her models, and she figured out that it is not possible to reproduce this enrichment if we do not take into account formation and deuteration of water in the prestellar cores. So the title that made the headlines at the time is that 30 to 50% of the water on our planet is older than the sun, which is definitely a very interesting fact. But I think that the most important result of this work is that if we consider that the formation of the solar system did not happen in extraordinary conditions, we can expand the conclusion of Ilse Cliff's paper and conclude that there is a budget, there is an amount of water in the prestellar core that is available to most forming planetary system. And water is not a molecule like any other. Water is one of the most important ingredients in the recipe for the formation of life. So this is a very clear link, this study is a very clear link between the prestellar core and the planetary system for a molecule that is of incredibly high importance. So prestellar cores are indeed very important, and these results could not have happened if we wouldn't have studied in great detail the chemistry of deuterated molecules in prestellar core. So it is really important to study the chemistry of these objects. So why do we use molecules in astrophysical tool? Why is dust not enough? Now this is a beautiful image of our galaxy seen by Gaia. You see that there is a very dusty dark lane towards the midplane. And if we switch our glasses and instead of looking in the optical, we look in the millimeter, in the sub-millimeter wave range, and in particular, we look at the emission of carbon monoxide, this is what we see. So this is a beautiful map of carbon monoxide, the 1-0 transition in our Milky Way. So it's the same image as before, just seen in molecular clouds. And then where it was dark, now it's bright. And this is why molecules are important, because in those dark lanes, that's where the molecular clouds are. The darkness comes from the dust, of course. And the dust is what allows the chemical complexity to grow by shielding the molecules. So if we want to see through the dust, we have to use molecules. The information that we can derive from the observation of molecules is multiple. We can, on one side, derive information on the chemical structure of this object, which is per se very interesting. The isotopic fractionation, which is also very, very interesting, especially if we want to look for evolution. And this is the example of the deuteration of water is a very, very important one. But we can also trace physical properties like temperature, density, the kinematics as well can be derived by looking at the line shape of a molecular emission. And even more importantly is that molecules are not homogeneously distributed in these objects, which means that if we observe the same object with different molecular tracers, and we know what we're doing, meaning that we know where these molecules are supposed to be, we can trace these physical properties at different depths within these objects, and then reconstruct the physical structure, and not only the chemical structure, but the physical structure of these objects. So this is something that dust does not really allow to do in the same fashion. So it's a prerogative of molecules. It's not easy, of course. You need to have quite a deep understanding of the chemistry and in order to understand the physics, and vice versa. So chemistry and physics are deeply interconnected in these regions, but it is a prerogative of the molecules. So how do we use molecules as a astrophysical tool? In order to do so, we need to put together the work in the laboratory, the theory, and the observation. So it's a collaboration between these three subgroups that allow us to use molecules as astrophysical tools. In particular, in the laboratory, from the laboratory, we need frequencies, high resolution spectroscopy in order to be sure that we are looking at the right molecule, reaction rates, broadening coefficient and collisional dynamics to do our modeling. Of course, we need the observations to see these molecules in space, both space and ground-based telescope, single dish and interferometers, depending on the angular resolution that is needed. And then, of course, we need the theory. Theory is what brings everything together, what allows us to connect to the big pictures, our single results, both for the physical modeling and for the chemical modeling. I added here also collisional coefficients here in the theory, which it's also in the laboratory. This is because it's particularly tricky to derive collisional coefficients from the laboratory, from experiments. So most of the collisional coefficients that are available are still derived from calculations. So that's why this is in both categories. So theory helps that where laboratory cannot go. So let's start with my own research. Let me introduce to you L1544. This is a prestellar core in Taurus. Prestellar core, once again, it's an evolved starless core. It's on the verge of forming a protostar, but there is not yet a protostar in the center. What you see here is the hydrogen column density map that I computed from Herschel Spire data at 3 wavelengths, 250, 350, and 500 micron. So this is the emission of cold dust in the region, and I can compute it together and calculate then the hydrogen column density, which is basically a proxy of the density itself. So this is the density structure of the core. Now, let me show you where this core is located. We saw before a beautiful map of our galaxy. So let's go back there. This is, again, our Milky Way, and there in red is where the Taurus molecular cloud is located. If we zoom in, now this, let me remind you, this is the carbon monoxide emission map, and this instead is, again, the hydrogen column density map derived from Herschel. So this is the Taurus molecular cloud seen by Herschel. What you see here are beautiful filamentary structure. You cannot really see it all because of the scale that I used, but one of the big legacy that we have from Herschel is that we know now that the filamentary structure represents a different scale, and this is basically the backbone of our molecular clouds, and it's within these filaments that stars are forming. So you see it very clearly here, and I think this is really beautiful. But L1544 is at the periphery of the Taurus molecular cloud. It's here. And I wanted to show you where it is because it's going to be important for the discussion of the projects that I'm going to present you now. So now we know L1544. What I've done is I mapped several molecules towards L1544 with the 30-meter telescope, and I mapped the central region of L1544, which is this here depicted with the dotted square. Among the many molecules that I mapped, 2 caught my attention in particular, and these were methanol and C3H2. This is the cyclic C3H2 with cyclopropionylidene that you see here in red, the methanol, and in black, the C3H2. Now, what you see here, these are the emission contours. So this here, so the central contour here is showing you basically where the emission of the methanol line is detected with a signal to noise ratio larger than 7, and the same for the C3H2. So it's basically telling you that the emission peak is here for the methanol and here for the C3H2. And this was peculiar because when I saw this, I was surprised because we were not expecting to see a segregation between these 2 molecules. Now, we do know that there is segregation between molecules, among molecules in L1544. We know that deuterated molecules trace very well the cold center of L1544, where the temperature goes down to 7 Kelvin. and the densities are quite high, up to 10 to the 5 molecules, 10 to the 6 molecules per cubic centimeter. We know also that nitrogen-bearing species are also tracing very well the dust peak, so the center of L1544. And we knew that more complex molecules, so like C3H2, like methanol, are tracing the outer shell of L1544, because while going towards the dust peak, these molecules, because of the low temperature, they will freeze out onto the dust grain. So they will deplete, they will be there, but not in the gas phase, which is what we actually see. So I was expecting to see them in the outer part, but not segregated. And one of the reasons that this is important is not only that we didn't know it, is that methanol is the beginning of the chemical complexity that we see in space. Is really the starting point from where the chemical complexity is built. And still to date, we are not completely sure why do we see it in the gas phases in prestellar cores. Now, I cannot go deep into this topic. I'm happy to explain more later if you want, but just keep in mind that we are still trying to understand. Am I the one writing here on the screen? Well, it doesn't matter. So just keep in mind that we are really, the community was surprised about 10 years ago when we detected methanol in the gas phase. And we are still trying to understand why. So what brings methanol in the gas phase? So I am plotting here the contours on this larger scale of L1544, and I showed you where L1544 is located, because in this paper in 2016, I argued that the chemical differentiation that we see in C3H2 and methanol was due to the larger structure around the prestellar core. And so towards the south of L1544, the Taurus molecular cloud is not there anymore. So this is really the edge of the Taurus molecular cloud, which means that the southern part of the core, the illumination here is quite efficient. So there is not much gas to shield the southern part of the core from the interstellar radiation field. And this keeps the chemistry young, which means that the carbon is not locked in carbon monoxide and it forms hydrocarbons like the C3H2. Methanol, on the other side, is kind of hiding from this steep decrease in density. And this is because methanol to form requires carbon monoxide, so carbon to be locked in carbon monoxide. And so methanol doesn't really like this strong irradiation. So this is what I argued in this paper, and it was rather qualitative. And what I did next was to, okay, so the two big results of this paper was, the first is that we could see a segregation that we were not expecting between these two molecules. And also, as I said, I was qualitative because it's difficult to be quantitative to explain these maps, as L1544 and other prestellar cores are modeled as spheres. And I cannot reproduce this asymmetry if I use a spherical model, of course. So what I did was then to test the result of this paper. I observed 6 additional cores in different evolutionary stages and in different environments. And I did that to see if the results that I was seeing in L1544 were actually an outlier, or if I was onto something. So if this segregation I could see and reproduce also in other environments and in other cores. Now I'm gonna, sorry, I'm not gonna show you all of the maps, but I want to show you one example, which is L1694-2. This is also an evolved prestellar core, like L1544. You see, like before in the color here, this is the H2 column density map, so it's the density structure of this prestellar core. you see it's very centrally concentrated, and then it has this tail, this shallower density tail here. In black, we have again the contours of C3H2, and in red, the methanol. And once again, like in F1544, the methanol is hiding in this low density tail, while the C3H2 is really tracing this sharper drop in density. So it is the same trend that I saw in F1544, and all the sources that I've observed show the same trend. So if I look at the maps in a larger context, I find that the large-scale structure around the prestellar cores have an impact on the segregation on the cores. Now, to publish this paper, it took quite a discussion with the referees. And the reason why is that, once again, I could not be as quantitative as I would have liked. And this is because there is no model that can help me reproduce these asymmetries three-dimensionally. So usually prestellar cores, when non-LT radiative transfer modeling is done, is only done towards dust peak, so towards one position, and then the core is mapped as a sphere. And this is, of course, something that doesn't help me if I want to model this. So finally, I managed to convince the referee, but this moving towards being more quantitative, it's of course always in the back of my mind. And for my next project, I decided to be a bit more quantitative. So let's be quantitative. In this project, which is something that I'm working on right now, and I hope to submit by the summer, I am studying methanol, in this case, only methanol, towards different offsets in different prestellar cores. This is a data set from the IRAM 30-meter large project GEMS. I'm using the methanol observation towards TMC1 and B213. So there are 3 prestellar cores observed in TMC1. So this here is TMC1C, this is TMC1, the ammonia peak, and this is the cyanopolene peak, which is TMC1CP. And this is the filament B213, another beautiful filament in Taurus. And you see here in the zoom all of the cores that have been observed. So towards each of these prestellar cores, there are during the GEMS large project, different offsets have been observed. So what I decided to do is to derive the abundance of methanol and carbon monoxide towards all of these cores in all of the offsets. So in this case, for a total of 90 offsets. And for the methanol, I used MCMC plus RADEC. So MCMC is the macro chain Monte Carlo algorithm, and RADEC is a non-LT radiative transfer code. So basically what I did was modeling together different emission lines of methanol and derive at the same time not only the column density, but also the volume density and the excitation temperature. And I did it for all of these offsets. I also derived the column density of carbon monoxide. In that case, as I only had one line, I couldn't really use the MCMC, which was also not as needed as for methanol, because the line of carbon monoxide has a lower critical density, meaning that it's not as sensitive as methanol to variation in the volume density that one has to assume in order to calculate the column density of the molecule without assuming the LT. So yes, so I have been more quantitative. I hope that my referee, if we will see this paper, will be proud. But the results are, well, let me show you. So these are the results. So here I plotted the column density ratio of methanol and carbon monoxide with respect to the visual extinction derived in all of these offsets from Herschel observation. Now I'm plotting methanol over carbon monoxide because the two molecules are chemically related. So methanol is formed from carbon monoxide. So That's why I use the ratio as a proxy. And you see here, there is not really a correlation. I've been really good in my analysis, but still there is no correlation. And also, if you plot, instead of the AV, if you plot the column density ratio with respect to the volume density that I derived for each of these offsets from the methanol MCMC Radek analysis, also there is not a correlation. So, what I did then was to look core by core at the maps and at the variation of this column density ratio to see if I could finally find some trends. And I do. Let me show you how. So this is the column density map, the hydrogen column density map of one of the cores in B213. This is B213 C1. It's in the north part of the filament. And these are the offsets, okay? And these are numbered, where one is always the dust peak. And here I am plotting in black is the column density ratio of methanol and CO. And in red and blue instead are the two different column densities of methanol and CO, which I plotted separately just to be able to see if one of the two molecules had more an impact on the final column density ratio. So what I see in C1, and not only in C1, but in the other cores in the northern part of B213, is that the column density ratio of methanol over CO is peaking towards the dust peak. And this is also true and very nicely seen in C5, another core in the north part of B213. You see that the column density ratio is peaking very clearly at offset 1, where offset 1 is the dust peak. And then there are the cores in the central part of B213, where the trend is slightly different because keep in mind the offset 1 is still the dust peak, but in this case, the column density ratio is peaking slightly with an offset with respect to the dust peak. And the same happens with C16, which is another core in the center part of B213. You see here, we are with an offset with respect to the dust peak. Now, let's look at the map of B213. So this is the northern part where C5 and C1 are located, the two cores where I showed you that the peak of the column density ratio of methanol and CO is at the dust peak. And this is the central part, which is where there are C16 and C10, which are two prestellar cores where the ratio instead peaks with a slighter offset outside of the dust peak. Now, the difference that there is between these two regions in B213 is that the northern part has way more protostars. So now they are not depicted here, but there are quite some protostars from class 0 to class 3 here in the northern part, meaning that the environment is the environment around the prestellar cores that I am studying is the irradiation is more efficient because of all these protostars. In the center part of B213, there are some protostellar cores, but it's not, they are not as, so the density of protostellar cores is way lower. So there are way fewer, sorry. So once again, my conclusion so far is not quantitative, but it's qualitative. Now chemical modeling is underway, which hopefully can give us some other constraints on this. Now, one thing that I want to underline here is that what I'm really trying to constrain are the the physical conditions that allow methanol to be in the gas phase in this course. And this is because methanol, as I said, is very important to start the chemical complexity in this prestellar course. Unfortunately, I think that what this study is showing, although these are preliminary results, but I think that what this study is showing is that just taking one cut along the prestellar core is not enough. And that's why the results altogether are so random, just one cut is not enough because the distribution of methanol in each of these cores will be asymmetric. So depending where you take the cut, it's going to make a big difference in the final result that you get. So, but stay tuned. This is still a project that is in divenire. Now, the future plans for this. I want to go from qualitative to quantitative, and I want to fill the gaps that don't allow me to be as quantitative as I would like. And this means deriving the three-dimensional physical structure of prestellar cores. So this is the project that my postdoc will work on from next month. And we will start from L1544, just because it's a very well-studied core. We have a lot of data, both dust emission and molecular emission. And so we will develop a method to derive the three-dimensional structure of L1544. And we will then use that not only to study in a quantitative way then the chemical structure of L1544, but we will also use it to then derive the physical structure also for other cores as a method. So just briefly, let's talk a bit about chemistry, even more chemistry towards L1544. This is another project that I worked on. So when I started talking about L1544, I told you that I mapped many molecules towards this core, and this is true. I presented my result in my paper in 2017. So I mapped several molecules, and you see here most of the molecules that I mapped divided in 4 categories, and these are categories that depend on where the emission peak is. So there are molecules that peak in the methanol peak, and these are all molecules that have oxygen. Molecules that peak in the HNCO peak, there is the dust peak and the C3H2 peak. Now, apart from dividing the molecules depending on their emission peak, just with a visual inspection of the maps, I've also in this work used the principal component analysis, which is a multivariate analysis method that it's used to study large data sets. It's very widely used in natural sciences. It is also used to study the interstellar medium. I think we will see more of this kind of analysis in the literature in the future. So what it helps is to find the underlying physics without having to do a detailed chemical modeling, basically looks for correlations in these maps. And what I could see is that the PCA was confirming this dichotomy that I see in the molecules in the methanol peak and the C3H2 peak. As you see, they anti-correlate beautifully in the result. But I could also see the molecules in the dust peak and in the HNCO peak positively correlating. So the PCA not only confirmed the grouping that I did just by visually looking at the maps, but it also underlined some correlations between groups that I would not have thought about. Now we are still working on understanding why there is a correlation between the molecules in the HNCO peak and in the dust peak. I think that the nitrogen is the reason why, but we are working on it. Now this analysis method, as I said, I think they will come more and more in the future. I want to present you one example that I think it was really nice to see. So this is not my work, this is from Vianney Taquet. He studied the different maps towards a low mass protostellar binary. And he didn't use the PCA, he used the K-means algorithm. And a difference with respect to what I did is that I mapped several different molecules and I used the PCA on all of those, while he used the maps of few molecular tracers. You see there is OCS, CS, SO, SO2, and a few others. But he mapped them in different transitions, so in different excited states. And this is very important because in protostellar core, of course, there is a wider variety of excitations with respect to prestellar cores. The future plans for this part of my work is to continue to use machine learning techniques, actually to use machine learning techniques more and more. And while with the first part of my project that I described to you, I want to derive the three-dimensional physical structure of prestellar cores. With this work, so with machine learning techniques, I want to use the large data sets that we have available here in the group, but that are also available online, to derive the chemical structure, so the three-dimensional chemical structure of starless, prestellar, and also protostellar core. This is something that we started already in my Minerva fast track group, and that we will continue with my PhD student that starts this fall. Now I want to conclude showing you again this beautiful picture of the evolution of material in the formation of stars and the planetary system, and mentioning again that there is a lot of complexity, a lot of chemical complexity, and my goal is to really find the chemical link to our astrochemical origins. So we have at the moment over 200 molecules detected in the interstellar medium. They're mostly organic. The level of complexity is quite high. You see here aminoacetonitril, which has been detected in star-forming regions in the Milky Way. And aminoacetonitril is just one step away from glycine, which you see here. And glycine is an amino acid, as the simplest amino acid. Now, glycine has not yet been observed in the ISM, but it has been observed in meteorites and in comets. And when meteorites represent the pristine material of our solar system, we know that meteorites have rained heavily down on our young planet for about 1 billion years. They could have brought the building blocks for the emergence of life. And just one little note, we over 200 amino acids, yes, 200 have been observed, have been detected in meteorites, and the life as we know it is the combination of only 20 different amino acids. So there is a lot of richness in chemical complexity out there. We are still far away from finding a link, a direct link with the emergence of life on our planet, but it's a nice path to walk, and I find it very interesting, and I hope that you also enjoyed the talk today. So I want to acknowledge my collaborators and you all for listening to me. Thank you.
Thank you very much, Dr. Spezzano, for this very exciting talk. I'm sure there are questions. There are already a few questions. So if anyone has a question, either use the chat or raise your hands, and then I will give you the floor. So there is already so there are already a couple of questions. So there is one question about so why we choose these two particular molecules for this study, and how can we be sure about the evolutionary stages of the clouds? So what are the levels of uncertainties? And what are the best explanation for the difference of the spatial distribution of these molecules?
Okay, so I guess that it's about the methanol and C3H2. So methanol is, as I said, the beginning of the chemical complexity. So it's the simplest complex organic molecule that we see. It has been chosen, and it caught my attention because of that. The C3H2 is a proxy for hydrocarbons. So these methanol and C3H2 are two different phases of carbon in the interstellar medium. One is the carbon locked in carbon monoxide that then becomes methanol, and the other one is the carbon that is not yet locked in carbon monoxide, and it's locked then in hydrocarbons like the C3H2. Now C3H2, the cyclic C3H2, is a widely distributed molecule in the galaxy. It has been observed in external galaxies. It has been observed everywhere. So it is a very nice and bright molecule to study hydrocarbons in space. So in terms of how to know the evolutionary stage of this course, L1544 and other prestellar cores are, so their evolutionary stage is defined by their chemistry, is defined also by how peaked is the density structure. So prestellar cores, evolved prestellar cores have a very, very sharp density decrease when you move away from the center, while starless cores, they are not so centrally peaked. And then in terms of chemistry, deuteration is one indicator. So high deuteration is an indicator that the prestellar core is very evolved. And the freeze out of carbon monoxide as well. It's a very good indication. So yeah. And what was the last question? Sorry, John, I don't remember.
So basically, what is the best explanation for the difference of the spatial distribution of these molecules?
Well, in this case, my explanation is still the illumination on the core. So the density structure around the core is what, in my point of view, explains much better the segregation if we look at the maps. Yeah. So
if I follow up on this question, is this a hypothesis that can be tested with other molecules as well? Is this something that would also change with the age of the prestellar core? Yes, so it depends on the molecules with respect to the age. So the C3H2 distribution is rather constant in the evolution of the core. For the methanol, no. For the methanol is more evolutionary stage dependent. We have been seeing this in many different cores. So yes, this is something that can be tested, it has been tested, but the data set, of course, this is not, the statistical sample is not as huge as the other statistical samples in our field, but because prestellar cores are not that common, the life cycle of the prestellar core doesn't last too long, while the starless core phase lasts longer. So it's we don't have too many objects to test this on. Okay, thanks. And just to be clear on definition, so when you say prestellar core is something that doesn't even burn deuterium yet. There is no star yet. There's not even there's not even no star yet. No, when I talk about deuteration, so these are all before the protostar is even formed. Okay, thanks. Okay, yeah, when I talk about deuteration, is deuteration in molecules. Thanks. So so moving on to the next question. So there's a question about a more technical question about the PSA algorithm that you use. So so can you tell us more about how you use it and what does the PS1 component that you showed represent? Okay, so that you don't show actually. That I don't show, yes, of course. So using this method, if it's quite, or any other statistical method or machine learning method at the moment with all of the libraries available for Python is relatively easy, especially if you have a data set that you know well. So my strength in this is that I was suggested during a talk to use this PCA on my maps. And it was easy to implement because these packages are already available, and it was easy to check if I was getting reliable results because I knew my data. So the first principal component, I'm not showing it here, is all of the molecules are positively correlating. And this is common in all of the studies that have been done with the ISM because it basically correlates with the density structure of the core. And all of the molecules are tracing the denser part of the core. So they all positively correlate. Okay, thanks, Sylvia. There's so I see that Costa Stasis is raising his hand. So Costa, you can unmute yourself.
Yes, hello. Can you hear me?
Yes.
Okay.
Hi.
Hi. Yeah. So Thank you for this very interesting talk, actually, and I'm very happy that you're working on the 3D structure of prestellar cores, especially because this is very close to my heart. I've worked on this problem back in the long ago, in the pre-pandemic era, right, in the dark ages of 2016, actually with my student. Aristrides, we tried to find chemical signatures of that would indicate the chemical signatures of the 3D shape of prestellar cores using a suite of numerical collapse simulations.
Mm-hmm.
And we identified a few commonly observed molecules that look interesting in terms of telling the difference between the actual intrinsic 3D shape, because of course there are all sorts of degeneracies when you look at it on the plane of the sky, right?
Yes.
And it turns out that your favorite molecules, C3H2 and methanol, are actually in our database. So in our chemical network, we have several we have several hundred molecules that we follow in a non-equilibrium fashion. So we solve the chemistry together with the dynamics, right? At the same time.
Interesting.
Not post-processing, right? And we do this for different shapes, and we try to see the differences, right? And so we concentrated on other molecules like CNOH and H2CO. But your favorite molecules, actually, the ones that you have data for, were actually in the simulation. We didn't pay much attention to them because back then we didn't know what to look at, right? We were trying to figure out something that would be useful. So let me send you, this is the paper, if you're not aware about
yes, please send me the link. This sounds interesting. Thank you.
So if you are interested, we now that you have the data, we can go back to the different models, take a look at the paper, and we can dig for exactly the molecules that you're observing and see what the difference in the shape is.
Thank you. Yeah, that's interesting. So this was non-spherical models.
Non-spherical, right?
Okay, that's good.
We are trying to connect the 3D intrinsic shape with what you see on the plane of the sky.
What I think it would be interesting and useful for these studies. Now, what I mapped is really just the central part of the prestellar core. But one thing that will be needed if we want to really model three-dimensionally the core is also the cloud-to-core connection. So we are working now of even larger maps of molecules that will allow us to see what is really the connection of the cloud, of the core with the cloud, because there is a connection. And sometimes, even nowadays, and even with L1544, that has been widely studied, we have trouble in reproducing the observed spectra if you do radiative transfer modeling, non-LTE, even just to the dust peak, to just 1 point towards the dust peak. Because, for example, now we have a PhD student who is working on the modeling of HC17O+, and we cannot reproduce what we see if we don't take into account an outer layer around the L1544 that contributes, that basically is absorbing. It doesn't contribute to the emission, but it absorbs. There is a self-absorption in the line, which is due to this outer envelope, because, and we have to be really careful there, because different lines will show this double peak or not, will show this self-absorption of not, depending on the critical density. So it is extremely important to really get into the details of the chemistry and the physics of this, and also remembering that the core is embedded in a cloud.
Yeah, so in these simulations in particular, we follow the collapse, so we don't put the core there, right?
Mhm.
And of course, there is a cloud. I mean, the initial conditions are we start from 1,000 particles per cc and a radius of half a parsec. So there is a cloud and a core that forms self-consistently with the chemistry, right? So take a look. I sent you the link in the chat. And
Thank
if you're
you.
interested, we can talk about it offline.
Thank you very much. Just a question, do you also derive the velocity structure?
Yes, of course.
Okay.
And exactly because this, again, this 3D shape is very close to my heart, because I really believe that if you can access the three-dimensional geometry of the cores, that tells you something about the dynamics and especially the importance of the magnetic field, because the magnetic field is a vector field and it breaks the symmetry, right? There's a symmetry breaking field. So we know that when the magnetic force is important, it acts perpendicular to the field, right? And as a result, it creates oblate cores, not prolate cores, right? So exactly for that reason, we have a suite of simulations, and we developed even a line radiative transfer code that can give you the lines from the simulations.
Awesome.
Given the velocity field, a non-LTE line radiative transfer code to post-process the results of these simulations, called Pirate.
Thank you.
So thank you, Costa and Sylvia. I think that's yet another reason to visit us here at some point. So are there any other questions?
I don't see my screen anymore now. Do you see my screen?
No, we don't. I think something happened.
Yeah, it happened that I wanted to open the paper that he sent me. Sorry, I will stop sharing and share again.
Okay, so I think if there are no other questions from the audience, I will actually abuse my power and ask one more question, and then we can finish. A very naive one, actually, hopefully. So in the beginning, you said something about the 30 to 50% of the water on Earth is older than the sun, and that is basically measured from the deuterium to hydrogen ratio.
The deuterium fractionation helps to model it, yes. So
okay,
we cannot reproduce the enhancement that we have in the deuterium in water on Earth and in the solar system if we don't, in these models, if we don't form water and deuterate it in the prestellar cores.
But when you talk about enhancement, you mean compared to what you see on the sun? So, or what you see in the interstellar medium?
It's compared to, well, in interstellar medium, depends where you're looking at. It's the cosmic,
sure, yeah.
It's the cosmic isotopic ratio. So it's something 10 to the 5, I think. And we have like 1 order of magnitude enrichment in the solar system.
Mm-hmm. Okay, thank you. So that was my question. So if there is nothing else, well, thank you, Dr. Spezzano, for this very, very exciting talk. It was a pleasure to host you online, and hopefully next time we can do it in person.
Looking forward to it.
Yes, and so thank you all for joining, and bye.
Oh, thank you.
Ciao.